Hello everyone. The title of this video is Homogeneous Linear Systems of Differential Equations, or DEs. And we're going to go over, in this case, in this video, the scenario where the coefficient matrix of our homogeneous system has some eigenvalues that repeat. Alright, eigenvalues that have a multiplicity greater than 1. Alright, so this is kind of also a continuation of, I had a previous video where I went over the scenario on, the distinct real eigenvalues. So I'm hoping you've watched that one, because in that one I discuss about, finding eigenvalues and eigenvectors corresponding to eigenvalues of a matrix. So in this video, I'm just going to kind of start off by showing you a part of a textbook that I'm looking at that discusses what to do, how to approach, just describing the general solution to a system when it comes to eigenvalues of multiplicity m. Alright, so I'll start off with that and then I'll get into a couple examples. Alright, so you're seeing here, so you see they describe up here what it means for an eigenvalue, say lambda 1, to be an eigenvalue with multiplicity m, and then the possible cases. Now, if an eigenvalue has multiplicity m, you may still be able to find m linearly independent eigenvectors, say k1 through km, corresponding to that value of lambda. And if that's the case, the general solution will contain a linear combination of, those k's times e to the lambda 1t. Right, pretty similar to what happened when you had distinct real eigenvalues. So if you have, so again, sometimes an eigenvalue has multiplicity m, and you're still able to find m linearly independent eigenvectors corresponding to that eigenvalue, which is fantastic. But that's not always the case, right? So case 2 is, well, what if there's only one eigenvector corresponding to lambda 1, and lambda 1 has multiplicity m? Well, if there's only one eigenvector, say k11 here, well then one solution will be like normal. It'll be that eigenvector times e to the lambda t. But then you have these extensions. Right? These could be found, I'm not going to get into this, I'm not going to go through the development of this, but these could be found through a, not necessarily like a reduction of order property, because these are already first order, but something similar to that. Again, I'm not going to go into it, just take the formulas here for what they're worth. So a second solution will take the form, some vector k, 2, 1. The vectors with different subscripts are different vectors here. They're all called k, but I might call them something else when I get into my examples. So another solution, the form it will take is some vector k to, times t, e to the lambda t, plus another vector times e to the lambda t. And then a third solution could be found, if we have multiplicity 3, a third independent solution would be, some vector k m1, or 3, 1 times t to the second over 2 factorial, t, t squared over 2 times e to the lambda t, and blah, 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 right? I'm not, in my examples today, I'm not going to see any eigenvalues with multiplicity higher than 2. All right, and for those of you in my courses or are taking my classes, I usually won't give you anything where the multiplicity of any eigenvalue is higher than 2. Yeah, because I mean it's not. It would just make the problem more tedious if anything. But so yeah, and I'll show you how do we find these vectors k21, k22, and stuff for these extra solutions. All right, so let's get into it. So my first example is going to be a 2 by 2 system. When I write this in matrix form, right, the coefficient matrix is going to be a 2 by 2 matrix. So we have dx dt, and I'm asked to find the general solution. Right? So dx dt equals 3x minus y, and dy dt equals 9x minus 3y. So I got these two unknown functions, right, x and y of t, that I'm trying to find that satisfy both of these equations. Now in matrix form, and should be pretty easy to write, this will look like this, vector x prime, which has the components x prime, y prime with respect to t, equals some matrix of coefficients of x and y, and I'll put them in that order. The coefficients of x down the first column, so 3 and 9. Coefficients of y down the second column, -1 and -3, times vector x. All right, and we're trying to find vector x that makes this true, where vector x, right, is equal to the functions x of t, y of t for components. All right, so if you recall from the last video, or again, hopefully you've been watching the videos I've been putting out. If not, don't worry about it, look them up, or find somebody else who has something similar on homogeneous systems. For a homogeneous linear system like this, we start off by, let's let x equal some vector k, times e to the lambda t. And I pop that in here, and then, we get rid of the e to the lambda t, and we end up, solving this equation, a minus lambda I, where I is the identity matrix, times these vectors k that I'm looking for. When is that equal to the 0 vector? And this would be called the auxiliary equation for this system. Alright, and the only way this has non-zero solutions for k is if this matrix A minus lambda I is singular, so if the determinant of that is equal to 0, and that's where I'm going to start. Remember the first step, again, I did this in the last video too. The first step in solving these systems using eigenvalues and eigenvectors is to find the eigenvalues of our matrix, and our matrix here is 2 by 2. Again, this is going to be matrix A. I'll call it A. All right, this matrix A that was mentioned down here. So first I find the eigenvalues of A, right, our coefficient matrix. Now in order to do that, I need to solve this equation for lambda. When is the determinant of the matrix A minus lambda I equal to 0? Right, because if the determinant of this matrix is equal to 0, then A minus lambda I will be singular, and the only way that means that this equation here has non-zero, non-trivial solutions for k. Alright, so I'll set this up. Now it's just a 2 by 2 matrix, and A minus lambda I, if you recall from last video, you just take the entries of matrix A and subtract lambda from the main diagonals. So that'd be 3 minus lambda, -3 minus lambda, down the main diagonal, and then every other entry remains the same, -1, +9 here. Alright, so this would be what? 3 minus lambda times -3 minus lambda minus, and then -1 times 9. And if I multiply this out here, this would be lambda squared. Then we have plus 3 lambda minus 3 lambda. So the lambda to the first power terms are gone. And then we have -9 plus 9. So this whole thing here is equal to just lambda squared. And we're asking, when is this equal to 0? Well, lambda squared, the only way that's going to be equal to 0, and these will be my eigenvalues. The only solution to this equation is lambda equals 0. but notice it's, lambda squared, so there are two factors that 0 makes 0 here, that this value of lambda makes 0. So this is a 0, this is an eigenvalue with a multiplicity, right, with a multiplicity of 2. All right. Right, so it's not like the previous video where I had, two different real eigenvalues. I have the same eigenvalue twice, right? 0 and 0 again. A repeated eigenvalue. Okay, well, so one of two things are going to happen here. One, I could, there may be two linearly independent eigenvectors corresponding to this, and that would be wonderful. Or there could just be one eigenvector associated with this, and then I'd have to go through and find a second independent solution, using the little setup on that book page, that website page I was showing you, and I'll show it to you again in a second. All right. So I found the eigenvalues for the matrix, the coefficient matrix. Now I'm going to find the eigenvectors. Find the eigenvectors corresponding to these eigenvalues. Now again, there's only one eigenvalue here. So for lambda equals 0, remember we're solving the equation now. We're trying to find the vectors k that satisfy this equation that I'm pointing at right here. We're going to solve a minus lambda I times k equals the 0 vector. And of course k equals the 0 vector works. I'm looking for non-zero solutions, right? Eigenvectors are non-zero vectors. Now if lambda is 0, this is just simply going to be a times vector k equals the 0 vector. We saw what matrix A was, right? It's this 3, -1, 9, -3. And don't forget, and vector k here, I could think it's a vector of constants, say k1, k2. So it's times k1, k2 equals 0 and 0. So remember the setup for this is already here, and I just need to put this matrix into reduced row echelon form, or RREF. You can do this with a calculator or some other piece of technology that you have. I don't care what. But this, the 2x2s should be pretty quick. If I were to multiply the top equation by -3 and add it to the second equation, the second equation would become a bunch of zeros. And then to get this in reduced row echelon form, have a leading coefficient of 1. The first non-zero entry in the first row will be 1. I multiply the top row by a third, get 1 here, and -1/3 here. And don't forget, this is like k1 minus 1/3 k2 equals 0, and then 0 plus 0 equals 0. Alright, so the first row has a leading 1 here. So the only column that doesn't have one of these leading 1s in it is the second column. Alright, so k2 is a free variable. I can let k2 be any real number I wish. So what I'm going to do is, as you saw in my previous video, I'm going to let k2 be some expression involving a parameter, say t, that can take on any real number value. Now because there's a fraction of a third here, I'm just going to let k2 be an expression that'll cancel that 3 in the denominator. So instead of having k2 be just t, I'm going to have k2 be 3t, for values of t that are real, right? I can let, this is free, I can have t be anything I want. Alright, and then if that's the case, then this first equation is k1 minus a third of k2. So minus a third of 3t would just be minus t equals 0. And solving for k1 here, k1 would be just whatever choice of t I make. Alright, so the solutions here, the solutions to this equation are, t times the vector 1, 3. All right, t times the vector 1, 3, where t is any real number I wish. And if you're talking eigenvectors, though, just make sure t is not 0. Now, the simplest of these is when t is 1. Right? Obviously, the simplest of the eigenvectors would be 1, 3. Right? So I'll call this k1. Right? If this was lambda 1 equals 0, we'll call this k1 equals the vector 1, 3. All right, so here's a solution. A solution to the system. Just a solution, not all of them. We're going to get to all of them. X equals 1, 3 times e to the 0t. Or just, what's e to the 0t? That's just 1 e to the 0. So this is 1, 3. So let's test that. Now again, this is just a solution to the system. This is not the end. All right. This is a 2 by 2 matrix system. So I've only found one solution. I need to find two. You should be able to find two linearly independent solutions to a 2 by 2 system. And the same thing goes for any n by n matrix system. An n by n system, you should be able to find, or you should be finding n linearly independent solutions, and then you can form the general solution by taking a linear combination. Now, if you want to test this, sure, let's check it out, and then we'll get to finding a second solution. So x equals 1, 3. So x equals 1, y equals 3. If x were equal to 1 and y were equal to 3, you'd have 0 equals 0 up top here, and then 0 equals 0 here. It satisfies both. Sorry, I'll pull that down a little bit. But if x were equal to x of t was just 1 and y of t was just 3, then dx dt would be 0, dy dt would be 0 because those are constants. And both equations would be true. This is a totally valid solution to our system. But there should be a second independent solution to this. All right. So how do we find that? All right. So this is that second scenario. Let me pull that site back up. This is the second scenario here where, we found that, lambda equals 0 was an eigenvalue with a multiplicity of 2. But we only found one eigenvector corresponding to it, right? That vector 1, 3. So we need to find another one. And, the first one, fine, I just did that one, right? I had 1, 3 times e to the 0t. Right? I found that first one, x1, I guess you could say. So a second solution, a second linearly independent solution, will take on this form, which instead of writing with the 2, 1, 2, 2 subscripts, I'm just going to use vectors k and p, right? Just different letters. All right, so getting rid of this. So according to what I just read to you there, if I want to find a second independent solution to this system, we'll have the following form. Has the form x equals some vector k times, t e to the 0t, which is just going to be t times 1, plus, and then some other vector, I'll call it p, times just e to the 0t. Right? Now if I just make e to the 0t 1, we have x equals, some vector k times t plus some vector p. Now look at what happens when I substitute this. We're going to try to figure out what these are. How do I find these k and p here? If I substitute this into the system, let me show you what happens. and I'm just going to go into any system, not just our system. Right, substitute into the system, x prime equals, and this is, I'm just going to write the matrix A just so I don't have to write out what matrix A is right yet. All right, we'll get to that later. But just know that this A here is that matrix. All right, times x. Well, if this is x, then x prime would simply be the vector k, because vector p is made up of constants. All right. So substituting these, we'd have vector k equals a times, and then this quantity, k times t plus p. Right. And then distributing the a, taking everything to one side, and getting the k stuff together. And again, we can think of this as k times I, or I times k, if you want to make this a 2 by 2 identity matrix. And we'd have the following. We'd have a minus I sorry. Oops, nope. Sorry. Getting the stuff with t together, not factoring out k. I have a times k times t plus a times p, and then minus k times I like that, equal to the 0 vector. All right. Well, I guess I don't even need the k times I. But still, the only way this is going to happen is if I equate coefficients. If a times k equals the 0 vector, and a times p minus k equals the 0 vector, so a times p equals k. Right? If a times p is equal to vector k, that would be the 0 vector as well. So I need both of these to happen. Now, if you look at this first scenario, that's what we saw just a minute ago. I saw that here. A times k equals 0. So this vector k that I mentioned here is an eigenvector of A corresponding to 0. K is an eigenvector of A corresponding to lambda equals 0. So k is just, I can just make that k the vector 1, 3, like earlier, any eigenvector. So we can have k here be, this k here be the vector 1, 3. And now we got to solve this. We got to solve a times p equals the vector k. Now we're solving a times p equals 1, 3. All right. Now again, vector A, or sorry, matrix A is the following. You have 3, negative 1, 9, negative 3. And I'm going to make an augmented matrix here with 1 and 3 on the other side. And let's just say vector P is made up of constants P1 and P2. And I'm going to be solving for P1 and P2. Again, pretty easy to put into reduced echelon form, reduced row echelon form here. It's only 2 rows. Again, if I do negative 3 times the first row plus the second row, I get the zeros here and 0 there, which is what I'm hoping for. I don't want 0 equals 2 or something, or 0 equals 5. That wouldn't be any good. And then multiplying the top by a third, I have 1, negative 1/3, positive 1/3. All right. And then just as before, let P2 would be the free variable here, equal 3t. And then up top, you'd have P1 minus t would be equal to 1/3, meaning P1 would be t plus 1/3. So the possible values of P are, infinite, because I could choose anything for t I want. So the possible values of P are, t plus 1/3 or 3t. Right. And so, I could let t be anything I want. Now, the easy one would be is if t were 0. Right, this is for any real number. If t were 0, I'll use that choice of P. Let's have P be 1/3 3. Right. But I think another one that'd be nice would be if t were 5/3. If t were 5/3, that would be nice, because then you'd have 2 up top. 5/3 plus 1/3 is 6/3. That's 2. And then 3 times 5/3 would be 5. You could use 2, 5 as well. Either one. I'm going to pick, I'll use this one just because it's easier with t equals 0. Maybe you wouldn't see this. So I got k equals the vector 1, 3. P equals the vector 1/3 3. And I put those in, and it gives me a second independent solution. All right, so a second solution to our homogeneous system is x equals, I'll call it x2, equals, remember, it's k times t. So 1, 3 times t plus p 1/3 3, or 2, 5 if you wanted. All right. And now that I have these two independent solutions, all right, there was one, just the vector 1, 3, and then this vector, all right, this solution here. I should call this x1. So x1 equals 1, 3. That's a solution to the system. x2 equals 1, 3 times t plus 1/3 3, or 2, 5 if you wanted. That would be another solution. And again, you can verify that that's a solution by going back to the original system and having x of t be t plus 1/3, and having y of t be 3t plus 3. And you would see that 3x minus y would be equal to the derivative of x, would be equal to would that work out? Dx dt would be 1. 3x would be 3t plus 1 minus that. I don't know if that works out so hot. Just a second. Okay, good. See, that's why I check your work. Went back and looked, and I said, hey, when I solve for p, so sorry about the jump cut there. When I solved for p, right, I had the t plus 1/3 3t, and I said when t was 0, we get 1/3 3. No, we'd get 1/3 0. My apologies. Now you could have also ended up with 2, 5 here if you let t be 5/3, but if t is 0, you get 1/3 0 for p, not 1/3 3. All right, so maybe you saw that earlier and you were like, hey, what the heck, you're probably screaming at the screen. So if x of t was t plus 1/3 and y of t was 3t, that would be a solution to this system. Yeah, dx dt would be 1. Then you'd have 3 times x would be 3t plus 1 minus 3t. Yeah, that 1 equals 1, that works out. All right, so 1/3 t, 1 over the vector 1, 3t plus the vector 1/3 0. Wonderful. All right, and now that I have these two linearly independent solutions, all right, I got the solution 1, 3, and this solution 1, 3 times t plus 1/3 0. The general solution to our system is any linear combination of those two. So x equals, some constant, say c1, times x1, right? So times the vector 1, 3, plus, and then some other constant, say c2, times x2. So times this, maybe I'll make this a bracket to like that, make it less confusing with all the parentheses. The vector 1, 3 times t, plus the vector, 1/3 0, or 2, 5, or whatever. Right? Or maybe even 1, 2, I don't know. Those would all work. Any value of p there. And there you go. Where again, c1 and c2 are any constants you wish. Right? Fantastic. All right, so that was that scenario where we had an eigenvalue with a multiplicity higher than 1, could only find one eigenvector that corresponded to that eigenvalue, and then had to go about finding other solutions of the following forms, right? And we only had to do a second one. Now, if you looked at other examples where you had an eigenvalue of multiplicity 3, but you could only find one eigenvector, then you'd have to find an x2 of this form and an x3 of the following, just replace m with 3 and you get the following form. And it would keep going like that for multiplicity 4, multiplicity 5, etc. But like I said, in most of my courses, my exercises that I assign and whatnot, things that I teach, I usually don't go higher than 2, right? Because you see it's already tedious enough. Okay. All right, so I've got just one more example. This was an example of a 2x2 system, right, where I needed to find 2 linearly independent solutions, and then the general solution was any linear combination of those. And my next example, the last example of this video, is a 3x3 system. So being a 3x3 system, I should be finding 3 linearly independent solutions. And then the general solution is, any linear combination of those. Okay. All right. So in matrix form, again, this would be vector x prime, right, with the x prime, y prime, z prime, equals matrix A with the coefficients of x down the first column, 3, 1, 1. Coefficients of y down the second column, -1, 1, -1, and coefficients of z down the third column, -1, almost wrote z again, -1, -1, and +1, and then times vector x, right, where vector x here represents, the functions little x of t, y of t, and z of t. All right, so as before, I would replace x with some vector k, some constant vector k times e to the lambda t, and end up with the auxiliary equation and all this. But our matrix A here, this coefficient matrix, is this 3x3. So again, first I find the eigenvalues of this matrix. So I'm solving this equation for lambda, right, the determinant of a minus lambda I, when is that equal to 0? All right, so I set up the determinant here. So I got 3 minus lambda, 1 minus lambda, and 1 minus lambda again down the main diagonal. And then all the other entries are the same, -1, -1, -1 here, and then 1, 1, -1. Okay. All right, so this is going to be a lot of algebra. All right. I'll just do cofactor expansion across the first row. So it's going to be 3 minus lambda times the minor 1 minus lambda, -1, -1, 1 minus lambda. Then plus 1, right, times the minor, because it's in the next first row, second column, that's in an odd position, so I do the opposite of the minor times that position. So that'd be plus 1. And then the minor for that is the determinant of this 2 by 2, 1, negative 1, 1, 1 minus lambda. And then minus 1, the first row, third column position times its minor, which will be 1, 1 minus lambda, 1, negative 1. Alright, and then keep taking this out. So we have 3 minus lambda times, now this determinant would be 1 minus lambda squared minus 1. So that 1 minus lambda squared would be lambda squared minus 2 lambda plus 1, but then minus 1. So I'd have lambda squared minus 2 lambda. That's all that would be left over in there, right? Because the 1 would go away. Right? So that's the determinant, that determinant. Plus this determinant would be 1 minus lambda plus 1. Right? 1 minus lambda minus negative 1 plus 1. So that's 2 minus lambda. Or the opposite of lambda minus 2, which I'll write in a second for reasons you will see. And then this last determinant, I'd have negative 1 minus 1 minus lambda. So that'd be negative 2 plus lambda. Right? Because I'd have negative 1 minus 1 plus lambda. So negative 2 plus lambda, or just lambda minus 2. Now I'm factoring each term. Now what I'm going to do here is I'm going to pull a negative 1 out of this, make it, lambda minus 3. Pull the negative 1 out. And I'll also pull lambda out of this factor, so we have minus lambda times lambda minus 3 times lambda minus 2. Or if I pull lambda out of this and a negative 1 out of that. So we have negative lambda times lambda minus 3 times lambda minus 2 for this first product. Then I'm going to pull a negative out of this second term, minus the quantity lambda minus 2, and then keep the last one the way it is. Now, this is also minus lambda minus 2. So I have 2 of these. So it's minus 2 times lambda minus 2. And then you might notice that both these terms, have a common factor of lambda minus 2 now, and a negative sign. I'll pull the negative out. So we have the opposite of lambda minus 2 pulled out. And when I pull that out, we have lambda times lambda minus 3 left over, and then plus 2, right? Because I pulled out a minus 1 from both those products. Okay, and then this hopefully turns out to be something nice, right? This is so negative quantity lambda minus 2, and then this is lambda squared minus 3 lambda plus 2, which does factor very nicely. That would be so negative lambda minus 2, and then this lambda squared minus 3 lambda plus 2, that factors to lambda minus 2 times lambda minus 1, so I have lambda minus 2 squared, and then times lambda minus 1. And we want to know when this is equal to 0. So now that I have the polynomial nice and factored, we get our eigenvalues pretty easily. Right. So I'll say lambda 1 equals 1. And this has a multiplicity of 1, so nothing to worry about here. I'll still have to find an eigenvector corresponding to this. This has a multiplicity of 1, right? There's only one factor of lambda minus 1. And then lambda 2 equals 2. But this, right, this has a multiplicity of 2. Multiplicity of 2. So it's this one that we're going to focus a little more on and see what kind of scenario we're in. Alright, so I found the eigenvalues of the matrix. Great. Now let's find eigenvectors corresponding to those eigenvalues. Right, so in part 2, eigenvectors. Okay. So first I'll do it for the one with the smaller multiplicity. For lambda 1 equals 1. So remember, we're solving the following: a minus lambda I, so a minus I times some vector k equals, when is that equal to the 0 vector? And we're solving for k, and here vector k, let's say, is k1, k2, k3. Right? It has 3 components because these are 3 by 3 matrices. All right, now a minus I. All right, what did matrix A look like again? So we're going to take matrix A and just subtract 1. Subtract lambda down the main diagonal. So taking away 1 down all these, you have 2, 0, 0, and then every other entry stays the same. So negative 1, negative 1, 1, negative 1, 1, negative 1. And then don't forget you have like times k1, k2, k3 equals 0, 0, 0. So if I put this in reduced row echelon form, I should be able to find the solutions of this system. Alright, now you can do this by hand using elementary row operations or with whatever technology you have. I'm actually going to do it with a calculator, a TI-84 Plus off to the side, and then come back and I'll have the reduced row echelon form written out here. So it's going to look like it's just flashed on the screen, but I'm taking some time to do that. I'll be right back. Alright, so here's reduced row echelon form. The first row has a leading 1 here, second row has a leading 1 here, third row has all zeros, great. The only column that doesn't have a leading 1 is the third column, right? So that means K3 is free. I'm going to let K3 be equal to T for whatever choice of T I wish, right? T is a real number. Then from the first row we have K1 minus T would be equal to 0, so K1 would be equal to T, and same thing for K2, right? From the second row, K2 minus T would be equal to 0, so K2 would be equal to T as well. So the solutions of this equation, right, the vectors K that make this true, are T times the vectors 1, 1, 1. And obviously the simplest one of these, which since this is lambda 1, I'll call that K1. The simplest one of these is when T equals 1 is just 1, 1, 1. Alright, so here's a solution to the system. I'll call it x1 equals 1, 1, 1 times e to the 1t. Alright, replacing lambda 1 with 1, lambda with 1. Alright, so this will be part of the general solution, and if you want to verify, you can check. Go back to the original system here and check to see that when x equals e to the t, y equals e to the t, and z equals e to the t, all these are true. Right. Okay. But again, I'll leave that to you to verify for yourself. Alright, so that was when lambda was equal to 1. Right. Now comes the trickier one. Right. Now I'm focusing on lambda equals 2, lambda 2 equals 2. This had a multiplicity of 2. So again, with a multiplicity higher than 1, for at least the examples I'm looking at, we're going to come across one of these scenarios. So again, either, there are some eigenvalues with a multiplicity of m for which you can find m linearly independent eigenvectors. Then you kind of just do it as if they were distinct. And we saw an example already of this scenario where we had an eigenvalue with a multiplicity of 2, but we could only find one eigenvector. So if you guess how my videos usually go, this is this case. We're going to see that, we're going to see that this eigenvalue of 2, we're going to be able to find 2 linearly independent eigenvectors. And then forming this general solution would be very simple in that case. All right. So let's do that. So again, we're doing eigenvectors. So for lambda 2 equals 2, for lambda equals 2, and we're solving the following equation. get matrix A back in the frame here. So we're solving, A minus 2i times, some vectors k equals the 0 vector. And what does A minus 2i look like? Well, let's just subtract 2 from all the diagonals of A. So 1, negative 1, negative 1, and then every other entry stays the same. And then I put this in reduced row echelon form. Now this one is very simple, because look, all 3 rows of this matrix are exactly the same. So I could just multiply the top row by negative 1, add it to the second row and the third row, turn those second row and third rows into a row of zeros. And the top row, its first non-zero entry from the left is a 1. So this is what you'd have in reduced row echelon form. So this time, a little different than all my examples in the previous video and earlier in this video, has 2 free variables, right? The first row has a leading one here. There are 2 columns without one of those leading ones. So there are 2 free variables. So k2 is a free variable, k3 is a free variable. And you could pick them to be whatever numbers you wish. So I can make that 100, make that 5,000, make this a billion, make that pi, whatever, and then solve for k1. So I'm going to let k2 be s, where s is some real number, and then k3 be some other number. I mean, they could be the same, but just make sure the expressions don't look the same, right? Because you can pick them to be different. So let's say k3 is t, where t is some real number. And then from the first row, we're getting k1 minus s minus t must be equal to 0, so k1 must be equal to s plus t. All right, and then our solutions to this system, the vectors k would be, s plus t for k1, s for k2, t for k3, and then we can break this up based on the free variables. This is the same thing as, if you remember vector addition, scalar multiplication. This is s times the vector 1, 1, 0 plus t times the vector 1, 0, 1, right, if you do the coefficients of t. And do you see now that and s and t can be any real number, as long as they're not both 0. If they're both 0, then we don't have an eigenvector. But do you see how we have 2 independent eigenvectors, 1, 1, 0, 1, 0, 1, for this eigenvalue with multiplicity 2? Alright, so if the number of independent eigenvectors is the same as the multiplicity, that is wonderful. Right? So a second solution, I could use this 1, 1, 0, a second independent solution, say x2, be 1, 1, 0 times e to the, and lambda was 2 here, e to the 2t. And then a third independent solution could be brought from this other vector, which is independent of this first one here. X3 be 1, 0, 1 times e to the 2t again, right? And there's no multiplication by t here. These are independent because of the vectors being independent. And again, you can verify that those are solutions of the system by plugging them into the system and seeing that all the equations are satisfied. And I leave that to you. And now that I have these 3, it's a 3 by 3 system, and I have found 3 linearly independent solutions. And if you want to doubly verify that they're linearly independent, you can do the Wronskian. Remember the Wronskian for these three solutions, where I've got these 2 here and this one here. All right, so take that, and that, and do the Wronskian. You'll see that the Wronskian is it's going to be non-zero for all values of t. But again, that's something I leave to you. Just trust me when I say all 3 are independent. So now that I have 3 linearly independent solutions to my system, we can state the general solution. Right, so the general solution of our system is the following. X equals, some constant, say C1 times, that X1 that I found, the vector 1, 1, 1 times e to the t, plus some constant C2 times this X2 here, times the vector 1, 1, 0 times e to the 2t, plus some constant C3 times my X3 here, the vector 1, 0, 1, again times just e to the 2t. Again, no need for t e to the 2t anywhere because I found those two independent eigenvectors. All right, totally different scenario than that first example I showed you in this video. And there you go. And again, if you want to verify it, go back to the original system, and you can either, scoot that down, substitute this into the matrix equation, or set it up where, x equals c1 times e to the t plus c2 times e to the 2t plus c3 times e to the 2t. x2 equals c1 times e to the t plus c2 e to the 2t, and then c3 times 0, nothing there. And y equals, and then z equals c1 e to the t plus no c2, and then plus c3 e to the 2t. And just again verify that all three of those satisfy all three equations. Alright, so again, a lot of stuff there. Solving these systems, you have to know how to find eigenvalues of a matrix, find eigenvectors corresponding to those eigenvalues. And I think the trickier one was that first example where if you have an eigenvalue with a multiplicity of m and you're only finding one eigenvector, then there was what I showed you on that page. You want to go back and pause that. All the different forms that the other independent solutions would take. And let me just show you one more time. Right, all these forms that you know what x1 one solution would look like, but then you'd have these forms for the other up to m solutions corresponding to that eigenvalue with multiplicity m. Okay, so hopefully watching me go over these couple examples help you out a bit when you're working on similar problems with repeated eigenvalues. And thank you very much for watching.